Okay, so let's start with the, that last big problem on the lab, okay? So, okay, so this is 7.5 meters tall. And so when that ball is clearing that wall, it's coming down here like this, and you're told that that angle is 28 degrees, okay? So here's the top of the wall, and that ball is coming down here like this. So, and it's traveling at, what did I say, 36 meters per second, okay? Pretty good clip, you know? It's a baseball, hit pretty far. So, Kara, what's the first thing that you're going to do with that 36 meters per second? And that angle?
Find the Vx and Vy.
Okay. So what did you get for your Vx?
31.8 meters per second.
Okay. And your Vy got?
16.9 meters per second.
16.9 meters per second. Okay. So visualize this. Okay. So here's this ball that's coming down like this. All right. But it still has 7.5 meters to fall. So here's the big idea, is that if you can find the vertical velocity when it lands here, that had to be the vertical velocity that it had when it was launched. You already know the Vx because your Vx isn't going to change. So that's 31.8 meters per second. That's 31.8. So when it's launched, you're at 31.8. So we already know the horizontal component over here. Okay, we've got that number. But what we have to find is the vertical component that it had here, which is going to be the same value as this vertical component when it actually hits the ground. Okay? So here's the deal. It still has to fall 7.5 meters. So when it lands, Shivani, when it lands, this is going to fall another 7.5 meters. Okay? So, and this is 2.5, so it has a ways to fall. So when it lands here, is it going to be going faster or slower than 16.9 meters per second?
Faster.
Faster, okay? So I know that this, when I launch it here, has to be bigger than 16.9 meters per second, okay? Because that's how fast it was when it was up there. So, what I'd recommend is that you use v squared equals c naught squared plus 2ab. Here's your initial vertical velocity, okay? So you've got this number. You know your acceleration, and you know how far it has to fall. So you can either make both of these negative, or you can make both of them positive. Doesn't make any difference. But this has to be like a positive value, so it gets added to this, so that you end up with a faster velocity. So you're going to crunch these numbers, put in 16.9, square that, add it to 2 times 9.8 times that 7.5 meters, take the square root of that, boom, there's your velocity. Okay?
Wait, okay, so when I did that, I got a number less than 16.
There's no way you did.
Well, when you did the V, because it's V equals 16.9 plus 2.
Squared.
Square root, yeah. So I got that as 12.8.
No, there's no way.
Yeah,
There's
we both
no way.
forgot to square root the 16.9.
Oh, that's awkward.
Yeah. Anyways.
But even so, you wouldn't have gotten them doing the way you guys are doing it. Well, I guess, never mind.
Yeah. So either make this negative 9.8 and negative 7.5,
Okay.
or make that positive and positive. It doesn't make a difference, but these have to have the same sign.
Mm-hmm.
Okay? Because otherwise, that way this gets added to that value squared. So again, you're going to add all those together and then take the square root of them.
Got it.
I don't know if
Mr.
that's-
Bergman, I
20.8.
never got a lab.
Yeah.
Huh?
I never got a lab.
Well, I sent it out yesterday, you know, with the video.
Oh.
There's the lab, there's the data that they had up at the top. So that's already written there. Yeah, you need to watch the video from yesterday.
Yeah, I was going to, I just didn't have enough time last.
Okay, well, and that lab was attached to it. So, there you go. All right. So then, once you get that, then you're going to put this over there, find that hypotenuse, find that angle. Okay? Kara, are we good?
Yes.
Okay. All right. So, let me kind of give you some hints about the last of the projectile problems, that assignment. Because we're going to have a very short quiz tomorrow over all of this. Okay? It's not going to be like a full-blown test. It's going to be basically some lemming problems, some ground-to-ground problems. That's it. So this is kind of like your review. So that answer to number 1 should be around 13 meters per second. Okay? Your answer to number 2, how far below it's going to hit, that should be around 0.3. Okay? It's an ish. Now let's talk about number 3, because if number 3 is wrong, everything else you're going to do is going to be wrong. So you got 47.8 meters per second at an angle of 38 degrees, okay? So again, the first thing that you're going to do is you're going to find your Vy and your Vx, and then never speak of that 47.8 again, okay? You're done with it. So what you should see is that your total time should be about 6 seconds, okay? So, you know that Vy, so what I'd sit here and go, okay, well if I go V minus V naught over G, that's my time up. So, on the way up, your final velocity is going to be 0. Your initial velocity is going to be that vertical component of the velocity. And you know that's going to be negative 9.8. So you should see that it takes about 3 seconds to go up, and another 3 seconds to come back down. So your total flight time is going to be about 6 seconds, okay? Because if you have that wrong, there's no point in going on with this problem. Then your maximum height should be around 45 meters, and your range should be around 226 meters, okay? So those are your 3 answers to number 3, okay? Your time's going to be about 6 seconds, your maximum height is going to be about 45, and your range is going to be about 226. Now, 226 meters, that's actually a pretty decent shot, because a football field is about 100 meters long. So this would be like about 2 football fields long. So that's a pretty long way to launch this paintball. Now, when you get to number 4, okay? So when you get to number 4, so you're trying to figure out how high it is at 2 seconds into the flight and at 4.5 seconds into the flight. The only way that you can do number 4 is if you do distance equals 1/2 AT squared plus V naught time. That's the only way you can do number 4. That has to be a negative 9.8 meters per second squared. You have your values of time. Now, this V naught, here's the most common mistake that's made. This V naught is that initial vertical velocity. It isn't the 47.8, okay? This is only the vertical component of the velocity. Because what happens in the x stays in the x, and what happens in the y stays in the y. Okay? So that has to be the vertical component of the velocity. That's it. Okay? Do not use the 47.8, do not use Vx, only use the vertical component of the velocity. So both of your answers to number 4 should be in the 30s. Bless you. Bless you.
Thank you.
Okay? So both of your answers to number 4 are going to be in the 30s. Now, when you get to number 5, okay? So, Bubba's going to shoot this ball, and the wall is 220 meters away, and it's 2.4 meters tall. Will the paintball make it over the wall? Now, here's the deal. At least he has a chance, okay? He has a chance because the paintball range is 226 meters, all right? So at least the paintball will go far enough. The question is it going to be high enough above the ground to clear 2.4 meters, okay? Which is about the height of the ceiling, okay? So here's what you want to do. So Matt, I know it's going to travel 220 meters, and I know the horizontal velocity. So what can I find out?
76. Well, did you hear me or is that wrong?
Huh?
Did you hear me?
No,
Oh, okay.
I didn't hear what you said.
Okay, good. I was like, am I wrong? The time?
Yeah, how are you going to get the time?
R equals Vx t, so R over Vx equals t.
Beautiful. So, you know range equals Vx time. You know how far you want it to go. You know the horizontal component of the velocity. So then you can find your time. Then what are you going to do with the time, Matt?
You're going to insert it into your v equals 1/2 at squared.
Beautiful. So that's, you're going to put that into distance equals 1/2 at squared plus v naught time. So take that, put it in here, take that, put that in there. Then you're going to see how high it is at that point. And if your answer is above 2.4 meters, which it should be, then it clears the wall. If it doesn't, hey, you didn't. Okay? So what you should see on number 5 is that he does clear the wall by about 2 meters. Okay? So you should see that it clears the wall. Now, let's talk about number 6. So you want to figure out how far back he can be so that it just clears the wall on the way down. Now, clearly, your answer to number 6, if you think about it, has to be between two numbers. It has to be less than 226, because 226 is when it's going to land back on the ground. Okay? So 226 meters gets you all the way out to here. You just want to clear this wall, so your answer has to be less than 226. But it has to be more than your answer to number 5, because on number 5 you were above this mark. So your answer to number 6 has to be somewhere between your answer to between that 220 meters on number 5 and that overall range of 226. So your answer has to be somewhere in between there. So ultimately, you've got to use range equals Vx time, okay? At the end of the day, that's what you have to use. You have to use range equals Vx time. Now, I tell you that it's already on its way down. So you already know from the very first problem on number 3, you found the time up, okay? You know the time up. So you know that's going to be about 3 seconds. Because you already found that number. So it's going to take 3 seconds to reach that maximum height. Okay? Got that? Now we've got to figure out how long it's going to take for it to fall from that maximum height down to the wall. So imagine this. Just forget that you're shooting a paintball gun. I imagine that I'm just going to drop a ball straight down. Okay? I'm just going to drop the ball. So if I just drop the ball, what's my initial vertical velocity? 0. And that's going to be the same thing. Even though it's on a trajectory, Once it starts to fall, your initial velocity is going to be 0. Okay? It's going to start at 0, and it's going to fall. Now, but it's not going to fall all the way down to the ground. It only has to fall to a point 2.4 meters. So what I have to figure out is, wow, how far does it fall? Now, here's the kicker. You know the maximum height. You found that maximum height up on problem number 3. You know that maximum height is about 44 meters. So when it starts to fall, it's about 44 meters above the ground. Okay? But it's not going to fall all the way down to the ground. It's only going to fall 2.4 meters above the ground. So, if this is 44, and this is 2.4 meters, how can I figure out the distance that it has to fall? Shivani.
You subtract it from the 2.40.
Beautiful. It's fantastic. Okay? So you're going to take your maximum height, subtract that from 2.4, okay? That's going to get you the distance that it has to fall. Then you can go to that, then it's just like a lemming problem. And then you can go, oh, time equals the square root of 2d over g. This is going to be the distance that it has to fall from its maximum height to the top of the wall. You know what g is. You can find your time. Add that to 3 seconds, multiply that by your Vx. So your time, your total time, okay, is just going to be a little bit less than 6 seconds, okay, which should make sense, because 6 seconds gets you all the way to the ground. So 6 seconds, it's going to be a little bit less than that, multiply that by Vx. So your answer to number 6 should be around 220-ish, okay? A little bit more than 220. Okay, are we good? Anything at all you want me to go over? Because we pretty much worked along anyway. Okay,
Wait, but
what, Kara?
number 5, when we said we can find the time,
Yeah?
but I thought the Vx was, like, that's the horizontal velocity.
It is.
So it's in meters per second.
It is.
But we were just given 220 meters and then 2.4 meters. Is it from the answers we already found before? In a different problem?
Yeah, that up there on
Okay.
number 3,
Okay.
you're gonna, yeah, it's that same, yeah. So you're gonna, to get your time, you're gonna take that 220 meters and divide it by that,
The range we got on 3.
no,
No?
your Vx. Because the ball, here's the path of the ball, right?
That's what I meant. I just got it mixed up.
Okay.
Yeah.
Yeah, so your time should be about 5.8 seconds, and then plug that into distance equals 1/2 at squared plus v naught time. Now are we good? Going once, going twice, so, okay. All right, so here's the next big unit. And it's going to be on circular motion. So we need to establish some ground rules first. So I'm going to take this rubber stopper and I'm going to get it moving around over my head like this, okay? So once I get it up to speed, okay, here's the first question that we have to establish this. Is the rubber stopper accelerating at this point? You all shake your heads no, that it's not accelerating. Why is it not accelerating? You say it's not.
As a constant speed.
It's at a constant speed. Okay? Now you just hold on to that thought. So I'm going to grab the camera. We're going to go to the back. So let's go to the back. We got to do a demo back there. Okay. Can somebody, I don't care who, kind of do some filming? Got it? Okay. So, here's what we've got. This is called a liquid accelerometer, okay? And no, everybody asks, is that like blood from a freshman? No, it's just water with food coloring in it, okay?
Sure.
Sure, let's go with that. Okay, so what I'm going to do is that I've got the string tied to the cart, and then I'm going to put like 100-gram mass on the end of the string, okay? Like so. Now, I'm going to let go of this, okay? This is liquid inside of here. So when I let go, is the cart going to accelerate? Why?
Because then it forces.
Right, I have an imbalance force, right? And the imbalance force is going to make it go this way. So it's going to accelerate because F equals ma. So since it's going to accelerate, there's three things that can happen to the water level inside of that accelerometer. It could just stay level, okay, because the force is acting on the cart and not on this, so it could just stay level. It could move towards the back, okay, or it could move towards the front. Those are your three options. It's going to stay level, slant up towards the back, slant up towards the front. So what's going to happen to it? Towards the back. Why?
Because it wants to resist the change in motion, so.
Beautiful, okay? That water level has, that water in there has inertia. It has mass. It wants to remain at rest. So when I let go of this thing, right? So as soon as I let go of it, Matt was right, that water level begins to move towards the back. So here's what I want you to see, is that the water level moves in the opposite direction of the acceleration. So the force and the acceleration are going this way, right? But the water level moves in the opposite direction. Now, imagine this. What if the very instant that I let go of it, what would happen if I could make this back section go away? At the very instant that I let go of it, this back section goes away. What would the water level, what would the water do? Yeah, it would just stay there. Okay? The water would just stay there, the cart would accelerate out from underneath it, and it would just fall. Okay? Because there would be no force to make it move, because that water wants to remain at rest. So here's what I want you to see, is that when I let go of that, okay, the water level moves in the opposite direction of the acceleration. And if it's not accelerating, what's the water level doing? It's just staying level. Okay? All right, y'all keep that in mind. All right, so let's go back up there. Oh, I'll take that. Thank you. We're walking. There's the room. Now, Kara, I'm going to need your help up in the front of the room for just a second. Okay, Kara, I need your help. Okay, just sit there. Beautiful. Okay, now just need you to hold that out like this. Yep. Okay, so here's the deal. So I'm going to take Kara, and I'm going to have her hold out the accelerometer like this, and I'm going to spin her around in a circle. Okay? But not fast. Okay? Right? So I'm going to make her spin around in a circle. Now, if you all said, when I had that rubber stopper going around like this, you all said it's not accelerating. True? So when I get Kara up to speed and I get her spinning around, and if that thing isn't accelerating, what should the water level do?
Not move.
Should not move. It should stay completely level if that isn't accelerating. Okay? Is that what you all think is going to happen?
Change my mind, I think it's gonna go to the outside.
Okay, I never said it was accelerating in the first place. You asked the question, I just kind of
Okay.
sat there confused.
All right, now, hold on. Now, Ms. Pfeiffer, you said it's going to do what?
It's gonna go to the outside.
Why?
Inertia.
Oh, inertia. Now, what does inertia want an object to do?
Stay at rest.
Or-
motion.
Stay in motion.
Stay in motion. Now, there's two parts to motion, right? It has magnitude and has direction. Okay, so let's see what's going to happen. You ready, dear?
Yep.
Okay, so if I give her that spin, what does it do? So it's going in towards the outside, right? Now, if I spin, I'm going to kind of spin you a little fast. Okay, you ready?
Yep.
Okay, if she's going pretty fast, notice that that water level is out there quite a ways. Now, as she slows down, what happens to that angle? It becomes less. Now, here's what's important. Which direction did the water move?
Outside.
Outside. So what's the direction of the acceleration?
Out the other way.
Remember, the water moves in the opposite direction of the acceleration. So my acceleration was acting towards the inside. Well done, dear. Thank you.
Thank you.
Okay. So here's the drill. So when I swing this around over my head like this, okay? Remember, there's two. Velocity is a vector quantity, which means it has what and what?
Magnitude.
Speed and direction, magnitude and direction, right? So here's what you all, up to this point at 8:15 on Thursday morning, April 1st, and no, this isn't an April Fool's joke or anything like that.
Oh, shoot.
I know. Up to this point, your acceleration has always been in terms of changing the magnitude, okay? We're making something speed up, we're making something slow down, okay? That's what we've been dealing with. But now when we're moving in a circle, now we're going to be changing the direction of the vector. So when this thing is swinging around, okay, and then when I let go of this thing, it's going to go flying off. So this goes into this whole idea of Jedi Stoffelwall.
Now I think I know why I was over
Yeah,
there.
that's what I was thinking.
That's a very real possibility. Okay? So when I stopped holding onto that string, it went flying off in a straight line. Because it's Newton's first law, is what Matt said, it's inertia. Okay? Because objects want to move with a constant velocity. And that constant velocity is the same magnitude and acting in the same direction. So if you change either one of those, if you make something speed up, slow down, or move in a circle, that requires a force because you're making it accelerate. So if you were to look down, and that's what I've got on those lecture notes, okay? At any given instant, that rubber stopper wants to go flying off in a straight line. So what we're doing is that we're forcing that velocity vector to change towards the inside, okay? That's what's making it change. So that's the direction that it's changing. That's the direction of my acceleration. So we're going to use AC, which stands for centripetal acceleration. Okay? Now, centripetal comes from the Greek word meaning inward seeking. Okay? Centripetal acceleration means inward seeking. So, what happens is that centripetal acceleration and the centripetal force, there's going to be two parts to this definition. That acts inward, okay? Always inward. Centripetal means inward seeking. And there's an and at a right angle to the velocity vector, okay? So when this rubber stopper is being swung around, that centripetal force and the centripetal acceleration, because your force and your acceleration have to go in the same direction, is acting inwards, and that's a right angle right there. So when I let go of it, it wants to go like this, and I'm forcing that towards the inside. When I'm over here, when I let go of it, it wants to go in this direction. My force is acting inward, and that's a right angle. So as that thing is going around in a circle, the centripetal force is acting inward. That's causing a centripetal acceleration that's acting inward. And there's no part to this. I promise you, I'm going to ask you this question. Hey, what's the direction of your centripetal acceleration? There's two parts to your answer. It's going to be inward, and at right angles to the velocity vector. Okay? That's it. That's what you got. All right. Now, math.
You.
Huh? I know. All right. So centripetal force equals mass times your centripetal acceleration. Okay, so that's the basic idea, right? Just like F equals ma, centripetal force equals mass times centripetal acceleration. So here's the problem, though, in terms of your normal experiences about centripetal force and centripetal acceleration. So let's say that Matt's driving his car, okay? And there's the steering wheel, and there's Matt, okay? And Matt being the safe driver, he has two hands on the wheel at all times, okay? Wouldn't look at his phone or be distracted, completely focused, right? Wearing his seatbelt, all that stuff. Now, Matt's driving along, and Matt's going to take a hard right turn, okay? So,
I do that too.
huh?
What?
He said he does that too.
I do that too.
Okay. Want to take a hard right turn?
Yeah.
Okay. Now,
Gonna whip it.
so this is looking down on top of the car, okay? So here's the car, and we're going to go like this, okay? Now, Matt, what do you feel is happening to you when you make that turn?
I want to pull the e-brake.
Okay? Well, maybe not that. But what does your body feel? Does your body
Wants to keep
feel
going
like
in that
you're
straight
being
line.
pushed to the outside or like you're being pushed to the inside?
The outside.
Okay, so here's the problem with centripetal force versus centrifugal force, okay? So centripetal force is going to act inward. But here's the problem. If you've ever experienced this, which I'm guessing you all have, like on a carnival ride or in a car, if you're Matt, I'm going to say, Matt, what did you feel? He's going to say, man, I felt like I was being pushed against the car door. Because you're going like this, right? And that car door, you feel like you're being pushed up against it. Or if you've ever been on a carnival ride, right? You feel like you're being pushed up against that car door. But here's the reality. What's happening is that your body just wants to move in a straight line. What you're feeling is the action-reaction force against the car door. You just want to move in a straight line. Okay? So, because if you think about it, and you say, well, I'm being pushed against that. Well, what would be the source of that force? There would have to be something inside your car generating a force field that you can't see that would be pushing against the side. So if you're Matt, right, here's the car door. So this force would have to be exerted from the inside of the car out. You can't see it. There would be no distortion in his clothes, okay? It isn't like we'd see like his shirt or jacket kind of begin to get like pushed down, okay? But what he feels is called centrifugal force. Centrifugal force centrifugal from the Greek word meaning outward seeking. So Matt feels like he's being pushed outward, but in reality, what's happening is that his body wants to move in a straight line. Now, it was somewhat analogous to if Kara was sitting here in the chair, and I came behind and I pushed her. So Kara would do this, oh, right? Now, there's nothing in front pushing Kara backwards. Kara's body has mass, it just wants to remain at rest. So what she would feel is the action-reaction force between the chair accelerating her forward and her body wanting to remain at rest. There's nothing in front of Kara pushing her backwards. She just wants to remain at rest. The same thing's going to happen with Matt, okay? Matt just wants to move in a straight line. The car door is just preventing that from happening. Now, we won't do this because we like Matt, okay? But imagine this. Let's say that Matt actually drives a Jeep, okay?
I do drive a Jeep.
Do you really?
Yeah.
Seriously?
Yeah.
Okay. So we're going to take your door off, okay?
Okay.
We're going to take the door off of his Jeep.
Okay.
We're going to take out your seatbelt because you drive a Jeep and you're cool, you don't need a seatbelt, okay?
All right.
All right? And then we're going to put in frictionless seats.
Oh boy.
So Matt's going to have no door, no seatbelt, and a frictionless seat. Now, Matt, you try and take that turn. What's going to happen?
I better have the grip strength or I'm gonna not be in the car anymore.
Yes, because now, are you going to be pushed outside the car?
No.
No. You're just going to go straight and the car is going to turn out from underneath you.
Mm-hmm.
Okay?
My car's in that.
So, when you talk about sources, and it's kind of a little bit poetic, sources of, God, I cannot spell today. I can't even spell forces today. How embarrassing. Sources of centripetal forces. The most common one that you use in your life is without doubt friction. Okay? So even, when you all walk to the back of the room, you all had to turn. Okay? Well, without friction, you all would just keep moving in a straight line. So, let's say that we had that like a big snowstorm, right? And Matt wants to take a turn. He wants to make that right-hand turn. So it's the friction between the tires and the road that allow Matt to make that turn. Because if this is a sheet of ice and Matt tries to make this turn, what's he going to do?
So if you drift it?
Yeah, you're just going to go in a straight line. Because if there's no frictional force, he's just going to move in a straight line. Now, so that's one of them. That's what you use almost all the time when you're driving or when you're walking, okay? So, Elise is playing soccer, right? And she's guarding Shivani, and Shivani goes that way, okay? So, she's running, and Elise is going, oh, I have to accelerate. So, she's going to push off her foot, right? So, even if you think of the experience of just running, if Shivani's going that way and Elise is going to try and guard her, she's got to accelerate. So she's going to push off that foot and go like this. Now, if the ground is a sheet of ice and you try and push off on that, you're not going to make it. Okay? That's why you all wear cleats when you play soccer, because that increases your friction, which allows you to accelerate more. Okay? So friction is what's going to happen most of the time. Now, the other thing that you can have, hold on. You want to rubber stopper back, okay, is tension, okay? You can have a string, you can have a chain, okay? Even if I just took this and like swing it around like this, right, that would be the tension in my arm. So the second one is tension. So the other thing that Matt could do, kind of a cool Indiana Jones thing, have you all seen the Indiana Jones movies?
No.
Okay? He's got the whip, right? So imagine that there's a telephone pole. So Matt realizes, oh, I got no friction. I am screwed. but I'm gonna do the Indiana Jones thing. So Matt takes the whip, wraps it around the telephone pole, holds on to it, and then slingshots himself around. And then when he gets to this point, he lets go of the rope, and he continues on a straight line. Okay? So that's another thing that Matt could do.
While steering the car.
Huh? While steering the car. Okay. Well, you might have to have Kara steer. Okay? Kara's going to steer the car. You're going to take the whip, pull it around, boom, slingshot around.
So I get saved, but Kara gets pushed out of the car.
Huh?
So Kara gets pushed out of the car.
Yeah, so yeah, then Kara gets, sorry Kara, bye.
Pushed out of the car. She just
Okay.
It's okay.
from out.
Come on.
I'm like, thanks, Kara, bye.
See ya. Okay, so tension's the other one. The third one is, anybody care to guess what the third one might be?
Gravity.
Gravity.
Oh my God, it's almost like it's written on this paper now.
Almost. Wow, how cool is that?
That's weird.
So here's the sun, here's this strange rock that we're on. Okay. And it really is, I mean, if you look at how the Earth is so different than the other 8 planets, and we're the only one that has like liquid water, you know, we're the only one that has any kind of condition at all, you know, good for life. So relative to our solar system, we are the strange rock, okay? So as the Earth goes around the sun, is it accelerating? Yeah, because if it wasn't accelerating, guess what? The Earth would do just what that rubber stopper would do. If we lose gravity with the sun, we're going to go off in a straight line tangent, and we're going to get awful cold and awful dark really, really fast, okay? So it's okay that we're falling towards the sun. That's a good thing, because the alternative is if we're not falling towards the sun, we're screwed, okay? Now, we have this little rock that orbits with it, otherwise known as the moon. The moon is accelerating because it's traveling in a circular path as well. So when you see something moving in a circular path, one of 3 things has to be happening, or a combination of 2. Gravity, the Earth, friction, your steering wheel, or you have a rope. Okay, that's it. Those are the only 3 things that can create centripetal force. So, let's talk math. So what's on your equation sheet is that you have centripetal acceleration equals v squared over r. Okay, so without going through the calculus, this is a rate at which your velocity vectors change direction. So if I know that this thing is going around and it's traveling at, say, 5 meters per second, and I know the radius, I can calculate that centripetal acceleration. So if you look at the units, you've got meters per second squared divided by meters. So you get meters squared over second squared divided by meters. One of the meters cancel out. I get meters per second squared. Okay? So it's the same units as linear acceleration. It's still meters per second squared. Okay? Pretty simple. Now, here's the deal. Because the velocity is squared, if I double the velocity because it's squared, what's going to happen to my centripetal acceleration?
4 times.
Yeah, it's going to go up by a factor of 4. If I triple it, it's going to go up by a factor of 9. So let's say that you're driving through your neighborhood and you take a turn at, say, 10 miles per hour. You look at your speedometer and you're going 10 miles per hour when you make the turn. You're still accelerating because the direction of your car is changing, right? So you have a constant speed because you're staying at 10 miles per hour, but you're still accelerating because you're changing the direction of the car. Now you go, wow, that was cool. I'm going to go up to 20 miles per hour and I'm going to try the same thing. Well, if you go up to 20 miles per hour, guess what? Your centripetal acceleration is going to be 4 times greater. Okay? So keep that in mind, because changes in speed make a huge difference in terms of your centripetal acceleration. Okay, now, this is the lab that y'all are going to start tomorrow. You're going to swing a rubber stopper over the top of your head like this, okay? And I want to figure out how fast that rubber stopper is moving. So what are some things that I can measure about that rubber stopper? I can measure time, right? What else can I measure?
The distance traveled.
Circumference.
The circumference, but I can't measure the circumference directly, but I could measure the radius. Now, how do you find the circumference of a circle knowing the radius? 2 pi r. So, when this rubber stopper is going around in the circle like this, we're going to go, and you all have done this. This is on the very first test that you all did. We said, oh, velocity is distance divided by time. And we said that's 2 pi r divided by t. Okay, y'all have done this calculation on the very first test you did. I said, oh, here's Mars. It's moving, it's spinning on its axis. How fast are you going? And you all use this equation. This isn't anything new. You all have seen this before. All this is, so when I swing this thing around over my head, okay, all this is distance divided by time. I'm just using 2 pi r to figure out how far it takes. And then this t, when you see uppercase T, that stands for period. That's how long it takes for it to get back to that point. Okay? So I can measure these things. And oddly enough, I'm going to get meters divided by seconds. Okay. Now, we're going to do a little bit of substitution. So we said that centripetal acceleration equals v squared over r. But we just said that we could find velocity using this. So I'm going to take 2 pi r over t, and I'm going to square that, and then I'm going to divide that by r. Okay, so this is like a pirate kind of thing. Arr, look at me, r's. So I'm going to square that, so I'm going to get 4 pi squared r squared over t squared divided by r. Now, at this point, the pirate kind of flips out, because I've got an r squared up there and an r squared there, so what's going to happen? What did you say, Kara?
Cancel.
Yeah. R. I'm going to lose one of the r's. Okay? So I get this. So centripetal acceleration also equals 4 pi squared r over t squared. Now, look at the units. I've got meters here divided by seconds squared here. Oh, I get meters per second squared. Okay? So there's two ways that you can do centripetal acceleration. V squared over r, 4 pi squared r over t squared. Okay? So this is how this plays out. So what I have up here is the green spinny thing. Okay? Ooh. And I have 2 quarters sitting on the green spinny thing. Now, I'm going to make them spin like this. Now, are the quarters accelerating when I got that thing moving like this? Matt, you shake your head yes. Why?
Because it's changing direction.
Yes. So the quarters are changing direction, so they're accelerating. So if you were to look at, like, here's the green spinny thing, okay? Here's 1 quarter, there's the 2nd quarter. Shivani, there's 3 forces acting on each quarter. What's one of the forces acting on the quarter?
Force gravity.
Okay, so we got gravity pulling it down, right? Okay. What's another one?
Force normal.
Force normal. Okay. Right? Now, they're moving in a circle. So what's the 3rd force?
Centripetal.
And which direction is it going to act?
Towards the center.
Beautiful. Okay? So my 3rd force is going to be my centripetal force. Now, what's creating the centripetal force? Friction, gravity, or a strain? Friction is, right? Friction is what's making these things go around. So here's what's going to be important. My centripetal force is created by my frictional force. Okay? That's what, because without friction, number one, if this was the magic frictionless surface, and I went to spin it, what would the quarters do?
Stay there.
Yeah, no, they'd just stay there. The surface would move out from underneath them, but the quarters would just sit there. Okay, they wouldn't do anything. So it's just like I have lost everything, my golf ball. Oh, dear, tennis ball. Oh, there it is. So if I put a golf ball on here, right, and I accelerate it out from underneath it, that golf ball, to a certain extent, stays right there because there's no force to make that thing move. Now, here's what we're going to do. I got 1/4 towards the outside and I have 1/4 towards the middle. Okay? Now, I'm going to get them up to speed like this. Okay? Which quarter takes longer to go around? The outside quarter, the inside quarter, or do they both take the same amount of time?
Both do the same amount of time.
Yeah, they both take the same amount of time. Okay? They both take the same amount of time. You're here, you're here. If I had Shivani time one and I had Kara time the other one, they would both get the same amount of time. So this is going to be important. T is going to stay the same for both of them. Now, here's what I'm going to do. I'm going to make this thing go faster and faster and faster. Okay? Which quarter is going to fly off first? The outside quarter, the inside quarter, or are they both going to fly off at the same time?
The outside.
What did you say, Elise?
The outside
Why?
has a bigger radius.
So what?
So there's more.
Yeah.
So there's more what? Oh, I thought you said something. There's more what?
Acceleration.
Great. So if you look at this equation, right? Centripetal acceleration equals 4 pi squared over r. They're both going to have the same value of t. So as the radius gets bigger, guess what? Your acceleration gets bigger. If they have the same value of t, and that's a huge caveat. If they have the same value of t. Now, friction, there's a limited amount of frictional force. Okay? Friction is not this, oh, it'll hold anything in place on the green spinny thing. There's a limit to what friction can do. Just like if I've got this string, okay, and this string breaks pretty easily, right? I can just pull it apart. I'm not going to tie this string to Hank the bowling ball, okay, and then try and swing Hank around in a circle. Okay? No, that's going to end so poorly for any number of reasons. Okay? So here's the deal.
That's our hypothesis.
Huh?
But our results might be different.
I feel like the string is just gonna break if you pull it.
Yeah, it's just not going to end well.
No, you haven't figured them
End well at all. So I don't have enough strength here in the string to make that happen. So, because there's a limit. So here's the deal. So your centripetal force is going to be mass times your centripetal acceleration, which is going to be 4 pi squared r over t squared. So as I spin faster, what happens to my value of t? I'm going to make it go faster and faster and faster. T is going to become smaller. So I'm going to have a constant top number divided by a smaller and smaller t. The centripetal force then is going to get bigger. But there's a limit to what friction can do. So I'm going to spin this up, okay? And as predicted, Miss Pfeiffer is right, the outside quarter fell off first. So when you're comparing these two quarters, okay, they both have the same t. Okay, that t is getting bigger and bigger and bigger for both of them. The outside quarter has a bigger radius, therefore that requires more centripetal force. Okay, so here's the last thing relating to friction. So if you look, let's just isolate that outside quarter so that we're not muddying the waters. So as Shivani said, I've got gravity, I've got my normal, I've got my centripetal force. So here's the idea. That centripetal force is equal to the frictional force, because that's what's keeping it on the green spinny thing. Okay? So if you look at mu equaling force friction over force normal. So this is where the magic is going to happen. So on that green spinny thing, the frictional force is what's creating the centripetal force. So I'm going to put that as Fc over Fn. Now, because I'm on a flat surface, I'm not on an incline, what does your normal force equal? What did you say? Oh, no. Well, it doesn't equal 9.8, but it equals the weight, right? Which is going to be mass times 9.8 meters per second squared, right? So on a flat surface, that's going to be mass times my centripetal acceleration divided by mg. So depending upon what you have, if you know what the centripetal acceleration is, these masses actually cancel out, and it's a ratio of just your centripetal acceleration to your gravitational acceleration. Okay? So there's a couple of ways you can look at it. It's force friction over force normal, which is going to be centripetal force over force normal, which is going to be centripetal force over Fg. Okay? Got it. Good? All right. So let me hand out your assignment right quick.
I still think we should just think the world.
Well, I don't.
Oh, this is like half the alphabet.
Okay. So let me explain what's happening on number 1.
Oh my goodness.
Here's a marching band, and they're going to try and move around in a circle. So you've got Betty Jo, and she has a radius of 1 meter. So there's Betty Jo. And then you've got Bobby Joe out here. And his radius is 8 meters. Now, notice that on all of these numbers, I've given you 3 significant digits. How many significant digits do you think I want in your answer? 3. Okay? So, they're both going to take the same amount of time to move around, okay, because they're going to move in a circle like this. So who's got to move faster, Bobby Joe or Betty Joe? Who's going to walk faster? Bobby Joe or Betty Joe? Bobby Joe is. Because Bobby's got to travel a much greater distance in the same amount of time. So Betty's going to kind of be like this, right? Kind of walking real slow like this. Bobby Joe, he's going to have to walk real, so he's going to be doing this action, right? He's going to be going boom, boom, like this. So he's got to go much faster to travel the same. He's got to travel a greater distance in the same amount of time. So make sure that all of your answers on number 1 have 3 significant digits. Now, when you get to number 6 on the back, this is like this rubber stopper. So number 6 is going to combine centripetal motion with a lemming problem. So let me give this visual on number 6. I'm swinging this rubber stopper around over my head. As soon as I let go of it, oh, that was a good one. Okay? It's going to turn into a projectile motion, and it's going to go like this. So you know how high it is above the ground, so you can figure out how long it takes for it to fall. So number 6, you're going to combine the lemming problem with centripetal motion. Okay? Start off with the lemming problem first, figure out how fast it has to be going, and then roll that into mv squared over r. So basically, you're going to find your Vx. Your Vx gets rolled into that. Okay? So if you're trying to figure out which one to use, okay? So if you're just given radius and period, just use this to use centripetal force. If you have the velocity, just use mv squared over r. Okay? All right, I'm done. You're on your own.